ඔසලයි මේ අපි සහස් මේ අයගේ ඉන්ටරැක්ෂන් එක දෙනකන් ස්ක්‍රීන් එක ෂෙයා කරන්නේ නැතේ මොකද මම නැත්තම් දිගටම අයගේ ස්ක්‍රීන් එක පේනවා මුලින් ඉඳන්ම
අය මම නැවතුවා
හරි මොකද ගන්න පටන් ගන්නවද අපි සිදු
පටන් ගමු
yeah but
Hello, good evening everyone and thanks for joining in. On behalf of the SLIIT FOSS community, we would warmly welcome you all to the live quarantine tech talk today themed Intro to Hacking Games. And we'd like to also extend our welcome to our speaker today, to Mr. Osanda Jayathissa, a security consultant by profession currently working in London. Without further ado, Mr. Osanda, the stage is yours to proceed.
Good evening, everyone, and thank you very much for inviting me. And I would like to thank Situm Sandeepa for inviting me in. And yeah, so let's get started. Can you guys see my screen?
Yes.
So basically, what I'm going to show you today is this is back in 2018, I just tweeted a small tweet saying that how I hacked this game called Minesweeper. Yeah, so this tweet really became kind of little bit got retweeted among people, and so many were asking me how I reverse engineered this and what was the approach behind this. So this is just the blog post that I posted in 2018, and today I thought of giving you a small introduction to how you can approach hacking a simple game. So first of all, I would like to just I will do everything on 2 VMs. One is my Windows XP, and the other would be on Windows 10 just for programming. So first of all, if we have a look at the game itself, it's in in the start. If you go to all programs and games, and you can see the game Minesweeper. And actually, to be honest, I really got no clue even up to now today, like how this game worked. I mean, like how to win this game at all. But so anyway, so what I actually did was I wanted to see how we can know the minefields. For example, if you just click, you can to see random numbers. You can see 1, 1, and here, that's it. There is a mine here. So first of all, if we have a look, if you analyze this program using a PE Viewer and see I have just, yep. So if we analyze the program, you can see in the optional header that this binary has no ASLR enabled. So if you look at the DLL characteristics, this binary has no, I mean, basically back in Windows XP, ASLR is not really a thing. I mean, starting from Windows Vista, you would say this dynamic base, this value. So it should be the image DLL characteristics with underscore or dynamic base. But anyway, even though it was compiled with ASLR, the OS doesn't support it. So the advantage here is the addresses are hard coded and the addresses doesn't change. So that's something good for us. And so first of all, let's kind of open the binary in debugger and see how it is functioning, and we can set some breakpoints. And first of all, let's try to analyze it. So if we have a look, we can see this is just disassembly of the program. So what I'll do is I'll first think about, I'll just look at the executable modules, and you can see if I look at what imports it uses, even from here, I forgot to show you the IAT, the import address table. You can see these are the APIs, this binary imports. So if we have a look, you can see there is this, you can see the advanced API 32.dll is being used. So you can see the registry APIs, and then there is GDI 32.dll, which is for the graphic device interface. So this is this was used in the past for doing graphic stuff like it's just it's a programming interface for graphical objects, and to transmit them for monitors and also for printers. So yeah, so we can these are the two main things that I focus, because I want to see what's going on. So we can see functions like there is functions like big BLT, and yeah, so let's have a look at first how we can hit a break. How we can place a breakpoint inside the registry values. So if I just go to, I can see reg create keyxw and the extended API, and I can see also the reg query xw. So what I'll do is I'll just hit the breakpoint in the reg query value x API, and also inside the reg create key ex API and the reg query value xw API. So yeah, I hit two breakpoints in the query value x and the create xw API. So basically, this create key x is used to create a registry key, and if the key exists, it's going to open the key value, and query is just for querying the registry keys. So what I'll do is I'll just execute the program. As soon as I hit the breakpoint, I can see it's trying to open and it's a sub key inside the HKey current key user called win-mine. So this is the part where it's going to read the registry keys. So what I'll do is I'll just open Regedit and go to this part. So it's inside the HKey current user software, Microsoft, and win-mine. It's inside win-mine. So inside win-mine. So if you look at these registry values here, you can see a number of registry values such as name1, the name of the, I think these are the high scores, it says the colors, difficulty, all the settings which the program loads are here. So if we just keep on going forward, we can see it's going to look for all the already played key. So the already played value is at 1. So and then it's looking for the height, width, difficulty, and mines, expose. This is the exposition value. Y sound, marks, tick, menu, time 1. It's the values for the time. It has 999. It sets the default times for the high scores, and it's getting name 1. So these are basically the values on the stack, which the API is actually part. I mean, when you are calling the API, the values are pushed on the stack, and we are actually reading from the stack. So, so yeah, you can see name 2, name 3, the color, and yeah, then the rest of the values are not from this. It's just a system registry key, so we don't really care about those. And so first hack, what I'll try to do is, let's see if you go to best time, so you can see it says anonymous. And what if I just go to this name, the first name, and I just put my name as the 3 names, and the time I'll just put 1, 2, and 3. Now if I just restart it and see the best times, I can see my name and 1, 2, 3 seconds. So basically we can just modify the high scores and almost the settings like difficulties and everything from the registry keys. And this is how we got our registry keys, by setting up the breakpoints in the 2 APIs. So this is the requery value and the create key. So yeah, so basically this is our first hack. And if there's any questions, please let me know up to now. Yeah, so let's continue to how we can actually map the minefield, like how we can actually get the values, or I mean, how we can get these values. I mean, how we can read these values and how we can read the mines before. So this is what we are going to try today. And for this, what I'll do is, first of all, I'll just remove these 2 breakpoints, like I don't need them. And So if I just go to the executable modules, and now I'm going to have a look at the Begin Paint API, which is used. It's the starting point of all the GUIs. So I mean, it's a place where a GUI would begin to start painting, or So what I'll do is I'll just go there and just hit the breakpoint inside that API. And if I just hit run, I can see that from where it was called. So it was called from here. So if we follow, I mean, I'm not going to take that much time about the reverse engineering process, because different people have different ways of approaching this. So sometimes it can be trial and error. Sometimes you might get lucky finding the exact place. So I'm just following a blind, like me, just backtracing how I can find the memory region where the map is mined. So if we start from the Begin Paint API, if I just put a breakpoint here and go forward to this function, which is going to call. I mean, it's going to pass this. So if I just step inside this function, I can see some important stuff going on. So what I'll do is, if I actually Yep. And if I just keep on stepping up, you can see the things are being drawn one by one. So yeah, so let me show that again. So if I just look, this is the first step where I drew the window. And if I just step inside this function, I can see these are the functions which will draw each part one by one. You can see this the background is drawn and the time is drawn, and the smiley face. And from here, this is the place where the minefield is going to get drawn. So this function, I could just rename it as drawing the mines. So actually, I'll just put yeah, maybe I just leave it like this, but because otherwise I don't want to get confused here. So if we just step inside this, we can see there are two loops. So basically there's a nested loop going on, and we can see the bit BLT API is used. This is used to transfer a block of I mean, this is used to paint a block, and this is a really important API which I'm not going to discuss that much. But in this case, and also if you have a look, the moment this loop starts, you can see it's going to move this value to EBX. So that's the place where our minefield should be. So if I just keep stepping up, you can see it's going to draw these mines one by one. So, and if you look at, so this is how it's going to draw the mine step by step. And if you look at the EBX values, as I showed you earlier, you can see this is the minefield, right? So this is the minefield, and if you look at these, this is 10 is just this arrow kind of value, and then it had this this 8F is the mines. That's the value of the mine is 8F. So this is the memory we are kind of actually weaving. So if I just and if I just take it out, and if I just click something, and if I look here, look, it just changes. So this is how we can hunt down the minefield. So this is exactly the place where our minefield is getting drawn, and this is the place where it has a logic. For example, number 1 is mapped as, if we have a closer look, as for 1 here. So this is AA is number 1, and yeah, like that is going. It got number 2 here for 2. So likewise, and so if I just click like this, and if I this is when you get bumped. So you can see all the values here. So this is a memory region that we need to hunt down, basically. So is there any questions up to now? All right, I'll just continue on how we can develop a program to hack this minefield. So I'm having Minesweeper here, the game. So I'll be using this. And first of all, we need to, we have to get a handle. We need to open the process, and we need to find, first of all, we need to find the window of the Minesweeper. So what I'll do, but before that, I just need to show you that this memory region is actually, since we don't have any ASLR, this is like the address doesn't change at all. So if I copy this value, and if I just open another one, and if I just go to something like any, you can view the memory address by any debugger. And if I just attach this to the mine, and if I just view the memory address, you can see this region, the FFF1010, and if I just give DA, you can see. But if I just hit go, and like this, and if I just press some values, and if I have a look, you can see the mine values exactly here. So this is constant. This doesn't change even you restart the computer. So this is the exact region we have to read from the memory. So what I'll do is, first of all, let's try to define the headers. So so the first things first. What I'll do is I'll just try to get first of all, we have to find we need to get the handle to a window. So what I'll do is I'm going to use this API called find window. So I'll just use a variable as window and find window and Minesweeper. That's the title of the window basically. So and also if the window is null, I'm gonna print out yeah, so this is the start. So if I just show you what this function does, it is just going to retrieve the handle to the top level window. So this is what the API I'm going to use here. So it's just a simple API, and I'm going to leave the long pointer class name as a null. And the name I have defined as Minesweeper. If you look, the title, it says Minesweeper, so I'm going to use this, and we can actually check. If I just compile this, yeah, it says window found. This is very mistake, but anyway, we found the window. So basically, it just found the Minesweeper window. So that's the first step. That what we should do. And next, what I'll do is I'm going to I need the process ID to open this process. So I'm going to use this API called get Windows thread process ID. Yeah. Basically, it requires a handle to the window and a pointer, I mean the address of a variable, just to have the process ID. So if we have a look at this API, how it works. So we can see it just retrieves the identifier of the thread that created that specific window, optionally the identifier of the process that created the window. So this API just, the return value just returns the identifier of the thread that created the window. But actually this is not the thing we are after this. So this is the place where it's going to a pointer to a variable that retrieves the process identifier. If this parameter is not null, the get window thread process ID copies the identifier of the thread to the variable. Otherwise, it does not. So this is the one which is important to us. We don't need any, they don't care about the return value, so I don't need to store this inside the variable. So I'll just put, I'm going to pass the window handle which we got earlier, and I need to define a variable to copy the ID. So I'll just declare it here. So I'm going to declare a variable here, and I'm going to pass the address of that variable here. So I hope up to now my code works fine. And if I just print it out, the DW process ID, and if I just run it, I can see this as 8. Let's just double check it. And this is correct, or oh wait, I need to actually initialize this. So that's the mistake I've done. Let's check now. Still it gets 0, so it's 8. Yeah, it's the PID is 8 actually. Yeah, nothing wrong with my code. It's just it is 8. So it's strange actually, because so I don't know how the 8 came, but anyway, so it's just one letter 8. Next, what I'll do is, since we got the process ID, so if I actually close this and open it again, and now if I check, it is 9060, and if I run it again, yeah, I can see 9060, which is our code is working fine. There's nothing wrong. So next, what I'm going to do is I need to read the memory. So what I will do is basically I need to use this API with process memory. So this is a bit of a long API, and actually if we have a look how this API works, so yeah, so this is basically it just copies data into a specified address range from the address space of the specified process into the specified buffer of the current process. Any process that has a handle with the process VM read can access. VM read access can call the function. So basically, this process is going to read the memory and copy it to a buffer. But the process should have the process VM read access control. I mean, this constant should be, this permission should be defined when you open the process. So it's going to take the process, a handle to a process. The base address is the place where it's going to start reading the process, and this is the buffer where it's going to copy that the amount of memory it's read, and this is a size which it wants to read, and this is a number of bytes read. And actually, we don't really care about it because we can leave this as null. So to use this API, first we need to open a handle with process VM read. So before that, I need to define the memory region that I want to read. So basically, if I start from 1005340 and go all the way down to this address, that is, 56A0. So I'll read from here to here, this entire memory region I'm going to read, because if you make your mind feel large, this entire thing will get filled, depending on difficulty level and the size. So I will define this region. So I'm going to define the start as 1005340. I guess I'm correct. 40 starting from here. Yeah, start from here. And then I'm going to define the end 0x 10056A0. I guess I'm correct with the values 40 and 53A0. So yeah, from here to here it's 56A0. All right, so we define the start and end. And also I'll just define the size as end minus the start. So this is going to be our size, where the amount, how much we want to read. In this, the difference is going to be the size of memory that we want to read if we subtract the end address and the start address. Yeah, so since now we have to actually get a handle to open the process. What I'll do is I'll just declare a handle, and I'll just call this process just for simplicity, and I'll just open process and give the access as it said. I should need process VM read. I need this permission, basically this access. And the inherit handle, there's nothing, false, and the process ID is that the process ID we just copied. So we are going to open that PID. We got from the get bin.thread process ID, and we are just going to get a handle to the process. And yeah, so in case the handle fails, I'm going to just write fail to open process, in case our process failed. And so the next thing I need to do is I need to use this read process memory. But before that, let's see if our process actually opened. Success. And if I just compile it, it says success. So we are basically able to open a handle to the process. So there's nothing wrong at the moment. No mistakes yet. And so next, what I'll do is so I need to actually constantly keep reading the memory, because each time we do something and it changes, the memory changes. So what I can actually think about is just write an infinite loop, maybe something like that. And now I can use this API. We'll be constantly reading in an infinite loop. And so let me think. So for this API to work, I'll have to actually allocate some memory. So before that, I'll just print the banner. And I will allocate some dynamic memory to copy the buffer. So if I just declare a long pointed byte, and let's call this buffer. So, and I'll just put local alloc, and I'll just put lmem fixed, no, fixed. And I'll just give our, basically we declare the size here, the size. So I'm going to declare, I'm going to dynamically allocate some memory based on the size. So it's going to allocate this much of memory, and I'll have to typecast this, of course. And so far, good. So just keep. And yeah, so let's read the memory now. So I'll just give how the handle to the process, and then I need to give the start. So it should be typecasted to a long pointed point, and the start is the place we are going to start the memory region, and we are going to copy the red buffer. We copy this to this we read from the memory, and we're going to copy this to this buffer, and we are going to give the size which is going to read, and then I'll give it this as null. And if this fails, I'll just print out fail to read memory. So yeah, and hopefully so far the program should work fine. So I hope there's no mistakes. And how do I know? How can I check the buffer read? So I'll just, what I can do is we can just write a simple for loop, and should be less than our size, obviously, and yeah, it should increment from here, and I'll just print the, and I'll just loop to our buffer. Hopefully this should work, and yeah, we can see our mine here. So if we check the hex values, it's very messy. We can see the FFFs, 1 zeros, 1 zeros, and 8 defs. So basically it seems like we are reading the memory region. So if we have a look here, it has FFs and the 1 zeros. Yeah, so basically it seems like it's working, but we need to actually beautify our core. I mean, beautify the memory region. So if you notice, this region has 16 bytes here. So here this is 16 bytes, and if I just make it expert and look, there is 16, 16, 32, and 30. From here to here, there are 33 bytes from here to here. So we can loop 33 and add a new line. So what I'll do is I'll declare a new variable called j, and increment our j, and I'll just type if j equals to 32. I'm going to add a new line. So it's going to add a new line, and I need to reset this to 0. So let's see now. So yeah, we can see it nicely, but if we make it see like this, you can look at the characters. So yeah, it just keeps looping, and we can see our minefield nicely. So we need some more work to be done. We have some more work. So what I'll do is I'll just add a sleep here, maybe for 1000 milliseconds. And what else I'll do is I'll clear the screen, and I think I forgot something here because I need to actually basically this should be inside here, not outside. Yep. Because we should be inside the infinite loop, and I should free our memory. That's something I need to do. I'll just free our allocated memory. All right. So let's try it now. So it's going to clear the screen each time, each 1 second. So we can see it nicely, and if we try to change something, yeah, it changes. So what we will try to do now is let's try to define some meaningful values to this, so we can view the memory region a bit clearly without that mess. So since we know some values, what we can do is I can just now, for example, if we have a look at here, these tens I can just print as stars, and these values I can just F values I can print as just dots. If buffer is equal to, if we find 0x F, I'm gonna print out a dot, else if our buffer is equal to 0x10, I'm gonna print a star. And now if we have a look, oh, wait a sec, I need to put else here. And now we have a bit of clarity. You can see it clearly now. Since I replaced those values to a human readable, but still there's a little bit more to do. I mean, since we want to read names, yeah, we need to replace these values as well. So what I'll do next is we need to print the mine. So the mines are 8F basically. If we, yeah, the mine values here you can see are the 8Fs. These two are mines. So the hex value is 8F. So I'll just copy this here. Make it 8F. And if it is a mine, I'll just put X here. And we can also define 40, it's just a blank space as a space, just a space. And it just, I'll copy this here. (41), 42, 41 is 1, 42 is 2, and 43 is 3. And if you put a flag, it's going to be 8E basically. So I'll just put the F here. And now if we compile, you can see there's a mine here. Put 1. I can see 1 here. Yeah, I can see all 1 ones. Yeah, all the 1s here and the 2s. And so if I want to win, I can just put the flag here. All gone here and here. Here the X says there's a mine. So there's a mine here, 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 and here. And there's a mine here. There's a mine here. There's one mine here. And near 2, that's it, I won. So this is how you can actually, read the minefield and win. So, and also, yeah, so I guess it should hit this highest score here. And our hack will work because since we have put the 32 by 32, I can just, even if I put the expert level, it will show nicely. And even if I go to custom and just increase this to 24, I don't know the max limits, but I just put 667 or something like that. It still works. You can see all the mines here. So basically, it's just our hack works in all ways. I mean, in any ways we can displace. So now what I'll do is I'll just show you some extra stuff where you can write to a memory. And what if we can write to a mine and change it to a flag? I mean, instead of X, I need to write, because mine is equal to 8F. So instead of that, I'm going to write 8T here. So for this, I'll have to use an API called write process. So if you have a look at this API, it's going to write, these two are almost identical. So we are going to write into a memory region provided. But the process should have process VM write and process VM operation access controls for this API to work. So first of all, let me add these two permissions to my open process. So we have provided the required access controls to our open process. And what I'll do is, if the process is equal to, I mean, you have a buffer. No, sorry, not the process. It's our, if our buffer is equal to 8F, what I'll do is I'll just write an 8E value, so it will become a flag. So right before that, let me first of all write this, and the value of the flag is 0x8e. So I'll just declare the value of a flag like f, and just say 0x80, I mean 80. This is going to be an unsigned SHA, and it's just 1 byte I'm going to write. So it's just 1 byte. And I'll have to give, I have to typecast this to LP void, of course. Before that, I need to give the header, the process, and I'm going to give the start of our, we need to give the memory address exactly where we're going to write. So it's going to be our start plus that the value inside the loop. That's the point where it detects this 8F, and to this place we are going to write from the start to this memory address. We are going to write, we're going to pass in the value of f, which is 0x80, and then I need to provide the size. So the size, I just give it a size of user. This is the size of the unsigned SHA, and the number of bytes, I don't care about it. Right, so if we programmed everything correctly, we should be able to now, whenever the loop detects a mine, it's going to write a flag. Let's say if our program actually works. So it's running, program is running, and if we just hit run, yep, you can see our mines have been turned into flags. So now I can just click anywhere I want, and I'm not, even though I click on the mine, I can't click on it because it's already a flag. So I can just click anywhere I want. I can win easily. Yeah, that's it. I just won without clicking on any flags. So our code should even work if I just go to custom and just put 667 and 50 is some huge value. And if I just put 50, and yeah, you can see it. It routes all our mines to flags. So Yeah. Yeah, so even if I click everywhere, it's going to be flags automatically. All the mines have been converted to flags. So yeah, so that's basically it about this is just the introduction on how you can approach reverse engineer. I mean, how you can reverse engineer and game and approach on hacking. I mean, how you can code a small program to read memory or write memories. And since we don't have ASLR, we are not calculating dynamically the address or anything. So those are a little bit, it's going to be a bit advanced, but since this is an introductory demonstration, this is how you can, go forward and, like hack some small games. I mean, have fun with hacking and, So if you have any questions, you can ask in the chat window.
Looks like people are a bit shy, Mr. Oshad, asking questions. If you don't mind me, I'll ask a question. How exactly did you get into actually hacking this? Like, what were your initial resources? Or how did you learn how to do this from the get-go?
Basically, it's like these kinds of reverse engineering kinds of things are like these things are basically like common things like we do, to crack a program and things like that. I mean, I was like, since I was small, I was really interested in cracking and how we can analyze programs and even malware analysis is the thing which I was really interested in. So all these fields have the same things in common, like how you can investigate how a program works, and you need to learn. You need to be very good at internals, Windows internals, and how you can program system, how you can program the system, things like that. And since I was actually since this is just my hobby, I don't do this in my work or anything. So since I was very interested in malware analysis and reverse engineering simple programs, I was like, whenever I feel like doing something new, I just take a program and try to analyze it. And I think there's one guy who has asked a question, I guess.
Yep. So he's asking whether it's possible to reverse engineer other games as well and hack it, if possible.
Yeah, of course. I mean, if you want to hack a commercial game like a proper game, we use cheat engine to analyze the values in the memory, and then we can write and read memory. But still, I mean, nowadays there are lots of protections, like memory protections, and the game hacking scene it's like a cat and mouse game. People find bypasses on how you can break these protections. And it's not, I mean, I have written some, you can check my blog for some games that I have written. I mean, not many commercial games, like little games that you can practice. And most of those cheats you have seen in gaming, in playing games, are using the same. I mean, they are using somewhat the same logic what we did here. You have seen like trainers. So these games use they use write process memory API and the read process memory API to read and write to the memory. So the cheat engine program is also very useful, where you can analyze where the values are in the memory, and that's basically it. I mean, this is basically, I mean, these things can be applied to anything out there, even the commercial games. But as I said, they are using lots of protections, and if you manage to bypass them, of course you can. Nothing is impossible, because this is like a cat and mouse game.
That's quite interesting. We'll see if there's another question. If there isn't, I guess we'll be wrapping up session. So we'll wait a bit more, see if anybody else has any questions. Looks like we don't have any other questions. So first of all, thank you, Mr. Osanda, for taking your valuable time and actually educating us on how to hack games. And it's quite an interesting topic, since, as you did sense. Actually, we actually have one more question. It says how to bypass. Bypass security.
It's a complicated. He's asking about lockdown browser. that's something because different. It's a different. It's a different thing. It's not a game. So different programs have different kinds of protections. I think there's no right one answer for it. So it actually depends on how the soft protection is.
All right. I guess we'll wrap up for today then. Thank you, Mr. Osanda, for your valuable time in educating us about this. And I'd also like to thank the audience for being courteous and asking like actual questions and being interested and being active during this session as well. So thank you, Mr. Osanda, for your time, and good night, everyone.
Thank you very much, guys.